Hello everybody, it's me Elena. Today we are going to talk about the essence of linear algebra, vector space and transformation. So let's start the topic. Please join us for a 15-minute deep dive into one of the most important ideas in modern computing, that is vector space and linear transformation. We will explore the theory behind them, look at the real world examples, and walk through a hands on Python implementation to how these concepts power everything from graphics to machine learning. So, at first, what is vector space? As we all know, what is vector space? So, just keep a short explanation about it. A vector space is a collection of vectors that follow two fundamental rules. That is, you can add any two vectors together and you can multiply a vector by scale. The most important condition is that after performing this operation, the result must still belong to the same set, a property known as closure. This means the space is self-contained and consistent under addition and scalar multiplication. Also, in the simple terms, a vector space provides a mathematical framework where vectors can be combined or scaled freely without stepping outside their defined space. This structure is the foundation of all linear algebra, forming the basis for understanding direction, magnitude, and transformation. Also, it plays a vital role in areas like physics, engineering, data science, and machine learning. Let's move toward linear transformation. So, what is linear transformation? Linear transformation is a special type of function that takes vectors from one vector space and maps them to another while preserving the structure of the space. In simple terms, it transfers vectors without bending or distorting them. Um, Linear transformation are fundamental in mathematics and computing. So they describe everything from geometric rotation and projections to complex data mappings in machine learning and computer graphics. Why this foundation matters? To know about this, these concepts form the foundation of many modern technologies. They serve as the mathematical backbone for 3D computer graphics, enabling realistic rendering, animation, and object transformation. Similarly, in scientific computing and engineering, vector spaces and linear transformation are used to model and simulate complex systems from fluid dynamics to quantum machines. In essence, this idea provides the tools that allows computer to understand, manipulate and visualize the world around us. The next is how we can visualize linear transformation in 2D. So let's understand how linear transformation can be done in 2D. It is the easiest when visualized. In two dimension, every linear transformation can be represented by 2 into 2 matrix, and applying the transformation simply means multiplying the matrix by the vector. Mapping vectors via matrix multiply. So in this, a transformation takes an initial vector to a transformed vector through the transformation matrix. Uh, as you can see, the example is already shown in the slide. So let's go through it. We can take the example for the 90-degree rotation. To rotate a vector 90 degrees counterclockwise, we use a specific rotation matrix at 90 degree. Here you can have the look for this. We have some of the key insights for preserving the structure. First one is origin fixed. The zero vector or the origin zero always maps to itself. Linear transformation cannot include translation or shifts. Second one is parallelism preserved. Lines remain lines and sets of parallel lines remain parallel after the transformation, demonstrating the preservation of vector space structure. And the last one is uniform scaling or sharing. Transformations apply uniformly across the entire space. A square might become a parallelogram or simply changing size, but it won't curve. Moving to the next we have Python implementation on defining and applying a linear transformation. How we can define and apply a linear transformation? We can do the implementation through the Python. The beauty of linear algebra is how easily it translates into practical code, especially using libraries like NumPy. We can define our transformation matrix and apply them to vectors or entire datasets with simple, efficient operations. So we have the number of steps for this. Here we have the step 1. Define the transformation matrix. For this, we use NumPy to define our transformation matrix. For instance, a shear transformation that pushes the x-axis horizontally based on the y. Again, we have the step 2. Define a vector or data point. For this, we have to define a simple vector which we want to transfer. For example, we can take an example, v is equals to 4 comma 2. After that, we have to apply the transformation in which the transformed vector is calculated using the dot product uh, function from NumPy, a highly optimized operation. Uh, at last, the result interprets where the original vector, the 4 comma 2, is mapped to 5 comma 2. The x component was shifted while the y component remained unchanged. This demonstrates a precise, predictable change across the vector space. This simple linear algebra operation is a fundamental building block for moving points in 3D games or adjusting data points in machine learning models. The simpler linear algebra operation is the fundamental building block for moving points in 3D games or adjusting data points in machine learning models. Here you can see all the Python implementation in the slides. Uh, so in summary about this, vector space provide the framework for working with vectors abstractly, and linear transformation describe how vectors move from one space to another while preserving their linear relationships. Together, Together, these concepts form the foundation of linear algebra and are essential for understanding systems of equations, computer graphics, quantum mechanics, data science, and many other fields. In conclusion, vector space and linear transformation form the backbone of linear algebra. Vector space provide a structured way to study sets of elements that can be added and scaled, while linear transformation describe how these vectors can be systematically changed or mapped between space. Understanding these concepts allow us to represent and analyze complex systems in a simple mathematical form using matrices. Matrix. Whether applied in solving system of equations, designing computer graphics, analyzing data, or exploring physical phenomena, vector spaces and linear transformation offer powerful tools for understanding and modeling the world through mathematics. This much for the video. Thank you so much. Hope you like this.